which is dedicated to optoelectronics, and I don't want to take too much delay, so I will do a very brief introduction. And we see that optoelectronic devices meet more and more microelectronics questions, and they are integrated in microelectronic devices, IoT devices, and their impact, especially on critical materials, are more and more pregnant. So we will talk about this and in this free presentation, and it will start with Lamia Mouloudi, which will talk about supply chain risk management methodologies for the nanoelectronic industries. So Lamia, if you can share your presentation, please, and activate your mic. Lamia, you are online? Lamia, I'm not sure that Lamia is online. So if Lamia is unfortunately not online, I don't know why, but Pauline, you are online, Pauline Oshkorn. Perhaps you can share your presentation, and if Lamia appears. Justine, could you please call Lamia to see if there is a problem with her?
Yes, I tried to call her. I don't have a response yet, sorry.
Okay, thanks. So let me know, and Pauline, if you can share your presentation, please. Thanks.
Can you see it correctly?
Perfect.
Okay. So good morning, everyone. I'm Pauline Oshkorn, and I will present you the work I've done in my thesis, which is about developing optoelectronic devices with reduced gallium and indium contents. So during this presentation, we'll see a few words about the context, the IoT places today in our society, why gallium and indium are considered as critical today for optoelectronic, the possibility of using 2D materials for answering the question of reducing the quantity of materials, the specific work on indium and gallium selenide for this thesis, and the two thesis strategies developed in parallel. So about the study of a model system on gallium selenide nanoribbons and the large-scale development of 2D layers. So as you have seen in the video before, the IoT is everywhere, and the number of connected objects evolve year after year, and it creates a lot of demand on material supply. Basically, IoT is based on acquiring, analyzing, transferring, and stocking data, and to do that, we need technologies using energy and materials. The general technologies are based on silicon for the microelectronic industry, but for specific application, we need other kind of materials. And specifically for optical sensors, emitters, RF, for example, we need 3-5 semiconductors. Among them, we have indium, gallium, antimony, and phosphorus, which are considered today as critical for several years now by European Commission. So there is a need in limiting and controlling the consumption of these materials, and you can do that either by substituting this material or reducing the quantities. In this thesis, we are working on elaboration and integration of 2D material in the goal of reducing the quantities. So why gallium and indium are considered as critical? So both are byproducts, which means that it's more difficult to extract them from the mines, and you have more steps in the production. That lead to small amount of producer in the world, especially for gallium. We've seen that for the 10 last year, more and more producers are closing, and now China is the main producer for this element. For indium, you have more producers in the world, but still you have two major producers, which are the Republic of Korea and China. For the application, both elements are really used in the optoelectronic for emitters, LEDs, laser, but also photodetectors, sensors, and integrated circuits. But indium has the particularity to be used in ITO, which is a transparent electrode used on all flat screen, which means that we use a big quantity of indium for this application. So as you have a number of producers that is limited, but also a use for this element that is really specific, it can create a criticality on this element. And today, it's really difficult to substitute this element and their compounds for optoelectronic application. So another way to do that is to reduce the quantity, and this is where the 2D materials are interesting. So those materials have been studied for the past 15 years, and in fact, they present really interesting properties, equivalent to properties for bulk crystal, but with really thin thicknesses. So you can find insulator, semi-metal, superconductor, or metal, for example. But here, the ones that interest us are semiconductors. You can find the TMDs, which are the 2D material really studied for optical application and which can cover between visible and near infrared for optical application. But you have also the 3-6 family, which is studied for several years now for optical application, and that can cover a large wavelength range between near UV to the near infrared. So among them, among the semiconductors in this 3-6 family, you have gallium selenide and indium selenide, which are considered today as potential candidates for optical applications. So which is interesting in this family is that you have different semiconductor with different band gap energy. So by creating heterostructure of this semiconductor, you can cover from UV to infrared wavelengths. So this is really interesting for optical application. And more specifically for gallium selenide and indium selenide, you see that the band gap energy evolve with the number of layers, which means that you can cover different wavelength range depending on the thickness of your material. And by creating heterostructure with this material, you can access to wide wavelength ranges. So this material have quite similar structure. They are layered semiconductor with tetralayer structure, which means that you have 2 metal atoms, gallium or indium, bonding with selenide indium, and between 2 layers, you will have weak forces, van der Waals type forces, and this is why we call them layered semiconductor. In the literature, you can find several demonstrators based on gallium selenide, indium selenide, or their heterostructure that have shown really interesting performances for photodetection application. But the major problematic is that most of the group are working with exfoliated layer. And this is a major problematic for 2D in general, is that we have a lack of large-scale, good crystalline quality elaboration method. And we also meet difficulties on integration this material with compatible CMOS steps. So for this thesis, we developed 2 strategies to work with this 2D material for large-scale integration, and we are targeting the photodetection application. To do that, we are working on a model system, which are gallium selenide nanoribbons, and on 2D layers grown on large-scale 200 millimeter substrate. So first, the gallium selenide nanoribbon. Those so nanostructure grows thanks to a catalyzed reaction. So we have a metallic catalyst which will react with precursor, which permit the growth of the nanostructure. Those are grown on 300 millimeter SiO2 substrate by MOCVD. And so typical nanoribbon obtained are shown in the picture B, and a close-up image of the kind of structures that we get is shown in picture C. So we have led a study on the growth parameter to control those nanoribbons morphology. So this was a multi-parameter study on the impact of temperature, growth time, and 6:3 ratio on the nanoribbon width and length, and also on the catalyst size and morphology. We also characterize our nanoribbon, and we have demonstrated that the nanoribbons present well-organized gallium selenide at the center of the nanoribbon. We never observed any defects in them, but we observe a thin amorphous zone on the edge of the nanoribbon, which is in fact an oxide shell coating the nanoribbon. We have led PL photoluminescence characterization on several nanoribbon and have found for every characterization one unique peak at 1.97 electrovolt, which is really near the band gap energy of the bulk gallium selenide, which is about 2 eV. To develop devices with this object, we need to transfer them from their gross substrate, where there are you have several nanoribbon, to a receiving substrate. So to do that, we drop cast our nanoribbon on a receiving substrate, and there you can contact one unique nanoribbon. And we have developed the steps to contact one unique nanoribbon by e-beam lithography. We have led several electrical measurements on different devices with and without elimination for different temperature. And we've observed for the different devices a photodetection behavior. We get nice results, but what we have observed is that we have a low dark current, but also a current under illumination that stays low even at high temperature. And our hypothesis is that our current level might be limited by a bad metal contact nanoribbon interface, probably due to the oxide shell covering the nanoribbon. So for now, we are able to synthesize high quality nanostructure by MOCVD on 300 millimeter substrate. We obtain nice devices showing photodetection behavior, which might be limited by a bad interface between metal contact and gallium selenide. So now we need to solve this problem. We also develop in parallel 2D layers on large scale integration. So to do that, we work on two types of growth. We are growing gallium selenide, indium selenide, and Zarito structure on silicon 111 200 millimeter wafers. You have typical TEM observation of a cross-section of indium selenide on gallium selenide on silicon presenting here. We're also developing growth on pre-patterned silicon substrates. So those are silicon 111 wafers, pre-patterned by SiO2 lines. And we have developed the growth of gallium selenide layer between those SiO2 lines. And here you have the typical TM observation of a cross-section of gallium selenide between two SiO2 lines and under Thai-gold contact. So here you have a low magnification SEM image of the gallium selenide grown everywhere, and in white you have the SiO2 lines. And so the idea is to use this particular growth to integrate our 2D material. So we want to take contact between two SiO2 lines to contact the gallium selenide. So we developed a vertical architecture devices using a metallic contact as top electrode and the highly doped silicon as bottom electrodes. We have led some electrical characterization, and for now we get some interesting results. So we want to continue and develop photodetection characterization on those particular devices. We succeed so to grow good quality gallium selenide continuous layer on the 200 millimeter silicon substrate. We have developed all the steps needed to integrate this layer directly on silicon, and we get first promising electrical characterization. So in conclusion, the objective of this thesis is to reduce the indium and gallium quantities by using the 2D materials and develop their integration for optoelectronic application. So to do that, we are developing two strategies. The first one is to work on a model system, which are the gallium selenide nanoribbon. We succeed to synthesis this nanoribbon on 300 millimeter substrate by MOCVD. We are able to control the nanoribbon morphology, and we have shown that they are high crystalline quality, and we get a nice photodetection behavior, probably limited by the presence of an oxide coating the nanoribbon. In parallel, we are working on 2D layers integration. So today we are able to synthesize gallium selenide, indium selenide, and their heterostructures on 200 millimeter silicon wafer by MOCVD. And we are developing now the synthesis of gallium selenide layers on silicon 111 pre-patterned substrate. And the growth is also done by MOCVD. We have developed the integration steps by developing a vertical structure. And in the continuation, we want to improve the quality of the contact interface between the gallium selenide nanoribbon and the metal electrodes to explore the photodetection possibilities that we have with this object. We also want to develop the electrical and photodetection characterization for the gallium selenide layers grown on pre-patterned substrate, and apply all the integration steps that we developed for indium selenide and gallium selenide heterojunction. Thank you for your attention.
Thank you very much, Pauline, for this interesting talk. So we have two questions, very interesting question from Jean-Pierre Raskin. So Pauline, as you said, gallium and indium are byproducts. From which primary elements are they byproducts? The first question. And the second question, gallium selenide and indium selenide based 2D semiconductors are of interest because you reduce the quantity of materials. But what about the processing energy to build up those devices compared with more classical devices relying on gallium and indium, bulk or thin film?
Okay, so for indium and gallium, they are both byproducts. So gallium is byproduct from the bauxite, which is used usually to do alumina manufacturing. And for indium, it's byproduct from zinc and copper, if I'm not confusing. About developing gallium selenide and indium selenide, so as we are developing really thin layer, I would say, and by MOCVD, which is a process that is used today in the industry, I would say that we are not consuming more energy. I would say maybe less because we are developing really thin layers, so it's shorter to develop this layer. So I would say that we are reducing the energy consumption, and the integration step, we are trying to use exactly the same kind of integration steps that you can already find for integrating the 3-5 element for optical application. So I would say we either will do the same or we do best.
Okay, thanks, Pauline, for this very precise and clear answer. And I agree with you. Perhaps it's more difficult for nanoribbon, but as the objective is to integrate 2D very thin gallium selenide and indium selenide layer, you're right. We should not consume more energy to integrate these materials. So I see that there is a new message. Need to compare silicon 111 need energy versus bulk gallium. Okay. Could you precise your question? Okay, I saw okay, Jean-Pierre want to know about the spot size of the laser illumination. So he said, I have highly strength silicon nanostructures that I would like to analyze. Oh, sorry. Analyze by PL to measure the band gap change. Could you discuss about the same later on? Sure. I answer for Pauline, but sure, Jean-Pierre, you can send me an email or send an email to Pauline, okay? Okay, to build gallium selenide on silicon 111, okay. So what was the question? Need to compare energy needed? Okay, you mean energy needed. So there is a question concerning the energy needed, I think, to elaborate the silicon 111 wafer in comparison with gallium arsenide wafer. Do you have an idea, Pauline, about the energy needed to make the substrate, I think?
No, sorry. For this, I
Okay.
don't know. I
Okay.
can say, I don't know, Thierry, if you know.
No, I don't have the answer, but I don't know. I cannot answer. We can have to make some research on it. Olivier, Pauline, as you know, electronic bond structures is a key property of 2D material, sure. Do you intend to perform characterization in order to investigate bond structures of your nice materials and related with optical properties? So,
yes,
yeah.
go, Thierry.
No, but I think it's ongoing, especially with XPEEM materials. So I think we have already some result, but we have to make more precise measurements to be able to investigate the bond structures. But you're right, this is a very interesting question. Okay, so I think if you have other question, you can contact directly Pauline or me, and I will send to her the question. Laetitia tell me we have to move to Enzo, and I agree. So Enzo, please, Pauline. Okay, Enzo.
Yes, hello.
Can share your presentation, and as you have understood, it's mainly dedicated to 2D material for optoelectronic application, and hopefully after Enzo, Lamia will present her talk. You confirm, Laetitia, that Lamia should present the talk after Enzo? Laetitia? Okay, so
yes, no problem. She's on. Everything's good.
Okay, thank you very much, Laetitia. So Enzo, the floor is yours. You can start.
Well, thanks a lot, Thierry. So can you see my presentation?
Yes, it's okay.
Yes, you should be able to see it. Okay.
Yeah.
So my name is Enzo Kloss, and I'm going to be talking about optoelectronics in two-dimensional transition metal dichalcogenides, or short 2D TMDC. So this is a collaboration between the Yale Institute of the CNRS in Grenoble and the CELETI, this part of project. So Pauline has already made a strong case for optoelectronics and 2D materials, but I'm going to summarize a couple of these things. So what can optoelectronics do for the Internet of Things and a more interconnected world than ever? Well, we need optoelectronics as an interface, as a means of communication between the real world and the digital world, actually. And the way we do that is, well, by, for instance, having photodetectors or LEDs, just some kind of device that connects the physical world with the real world. So we get information from one part to the other. Now, many of the current devices are based on 3-5 materials. Pauline has already pointed that out, and there are certain problems with the current materials that are being used. So political dependencies, their environmental impacts in mining countries, and very many others. So for us, the question has to be asked, okay, can we substitute these materials? And our answer to our approach in this case would be using 2D materials. Now, to understand what 2D materials actually are, you have to back up a little bit. This is a bulk. This is an illustration of a bulk graphite crystal. Now, graphite is made out of carbon. And as you can see here, these carbon atoms are crystallize in a sort of layer form, where inside one of these layers or these carbon sheets, the carbon atoms are very strongly bound to one another, but in between the sheets, they're rather loosely bound to another with much weaker forces that we call van der Waals forces. Now, in 2004, the researchers Novoselic and Geim were able to extract what they called graphene, that is a monolayer sheet from this bulk graphite. Now, how did they do that exactly? They put this bulk graphite onto some scotch tape, put the scotch tape on, then they pulled off what is called a monolayer, or what they then called graphene. And that's not all. When they started looking at the optoelectronic properties of this graphene in comparison to the bulk crystal, they saw that, well, the bulk crystal is a strong conductor, whereas the monolayer crystal is a semi-metal. So they noticed that there was a radical change in optoelectronic properties, and that really triggered the discovery and a new field of 2D materials. And many 2D materials have been discovered since, which lies in the same fashion, just like the TMDCs. So the TMDCs, the transition metal dichalcogenides that I'm concerned with are MOS2, WS2, MOSE2, and WSE2. So they also crystallize in this form of layer structure, where you have the layers coupled to one another by van der Waals forces. But here the molecule is a little bit different. So you have a transition metal that binds with two chalcogens, making it a 3-atom molecule, actually. But other than that, it's in terms of structure, it's similar to graphene. So what's particular about these transition metal dichalcogenides? Well, it's the optoelectronics, actually. So you see this graph, which shows us the photoluminous intensity, study of Mark and others on MOS2, where they compared the photoluminescence intensity between a bilayer system, which you see is almost absent, and a monolayer, which is very strong in this case. Now you have to ask yourself the question, why going from 2 layers to 1 layer is there such a strong photoluminescence? And that can mostly be answered when we look at the internal band structure of the material. Now, what is a band structure? There is first of all a diagram, this kind of diagram, which has 2 axes. So it has an energy axis. It also has an x-axis, which we call the wave vector, so to speak. And now there are different lines here, and these lines are nothing but positions, so values for the energy as well as the wave vector. By the way, can you see my cursor? I'm not sure you can see. Can you see my cursor?
Yes, yes,
No?
we can see it.
Yeah,
yes.
okay, all right. So there are positions for energy and the wave vector at which an electron is allowed to exist. Now in a bilayer system, we can make it so that an electron occupies this band, for instance. And now electrons will want to lower their energy at some point, so it could possibly travel over here to a lower energy. However, it cannot do that by emitting a photon, because there's a rule that says, well, if an electron wants to emit energy and by emitting a photon, it has to do so by not changing its wave vector. So here the wave vector is obviously changed by going from one band to the other, so it cannot emit a photon doing that. Now in a monolayer system, the situation is a little bit different. If we make it here so that we have an electron here, well, the next lowest band is right underneath it. And in that case, well, the electron can lower its energy by emitting a photon, and now this rule is actually respected. So here a photon can be emitted, and that's why we have the strong photoluminescence in monolayers. So another way to quantify this is to look at the difference between this band here at what we call the gamma point and the K point. And you see that here there's a positive difference between those 2 bands, whereas in the case of the monolayer, it actually switched signs. So it's different now. So you could say that in monolayer TMDCs, by switching this value, E gamma K, you suddenly have strong light absorption or emission. And that is what makes this strong photoluminescence. So what can 2D materials do for our optoelectronics? Well, so this monolayer thinness does a couple of things. We get new optoelectronic properties. We've seen that with graphite and also bulk TMDCs. We use very, very little material. We get mechanical flexibility. So these monolayers or bilayers are very flexible. And then as further, these 2D materials become very sensitive to the environment. So what this does is that a 2D layer system will actually be very sensitive to what's above and what is below it. And that allows people to build completely new optoelectronic systems by changing the environment. One way they have done that is by combining, for instance, the group of Hu and others have combined graphene, HB, and WS2 to build a light emitter, whereas Sistra and others have combined graphene and WS2 to build a photodetector. So first prototypes are being done as of this year. So we asked ourselves the question, okay, so can we change the optoelectronic properties in particular, such as the band structure here of a monolayer TMDC when we change its environment? And to answer this question, I fabricated multiple samples. So these samples that I'm going to show to you here are monolayer WSE2, so a 2D layer built on HBN and also NSI, and this on 2 different samples. And I was also given data by a sample that was built by Yamashita and my supervisor Renaud, where a monolayer WSE2 layer has been put on substrate of SiO2. So 3 different environments as a whole. This is what optical microscopy images of these samples look like. So we have the SI with different markers to find ourselves. Because this is in the micrometer scale, we need those markers. And then we have our HBN layer, and I put WSE2 on top. And in both cases, the WSE2 touches both the HBN, but also the silicon substrate directly. Now, our means of analyzing these kind of structures is by case-based photoemission electron microscopy. So we're interested in getting band structures. How does this work exactly? So we have our 2D layer system, and we shine highly energetic light onto our system. Now the light is so energetic, in fact, that it's enough to lift electrons out of this system and make them photoelectrons so that they're exiting the sample eventually. What we can do is about these electrons that leave the material, we can measure three things: the location that they stem from, the angle at which they're being irradiated, and also the energy, the remaining kinetic energy that these photoelectrons then have using an energy filter. Now in a scheme, this would look like this. So we have our electron at an original state. We then lift it with the energy of the photon to a higher state, and then we can measure the remaining kinetic energy as well as the work function that gives us the binding energy. So because energy is conserved, we can then get the binding energy. But another quantity that would be conserved in that case is the wave vector, actually, which we can refer to by simply measuring the angle. So since we have the binding energy and we have the wave vector, we have everything that we need for building our band structure. Now, we can build the band structure, but we can also do microscopy, real space imaging using secondary electron images in this PEEM method. So you've seen these optical images where the contrast is not so great, but when we pass to actual PEEM images, then it becomes a lot more easy to see. So here I have my HBN layers with WSE2 monolayers, and you see that, well, there are 5 different zones of interest that I've analyzed for those 2 samples, actually, which I've marked here with the circles. So I was interested in this parameter called E gamma K on different substrates, silicon, HBN, and SiO2. So I've looked at them, and here I'm going to show you different photointensity lines. What I've done is here between gamma, the band at gamma, and the band at K, I've done a cut. So this peak here is the band at gamma, and at K we have a spin splitting, so you see 2 peaks here actually. So now we compare these cuts, these energy distribution curves for the different substrates, and what we see is while K, the K split band, the bands at K remain roughly the same, the band at gamma actually moves on the different substrates to different positions. So that makes it so that this energy difference, E gamma K, actually changes from 400 to 500 to then 700 millielectron volts going over the different substrates. And we looked at possible mechanisms why this could actually be. So thinking, okay, maybe the substrate is straining or mechanically stressing our monolayer TMDC. So this could be an answer why we see this change in the band structure. Another would be, okay, maybe there are positive or negative charges being transferred by our substrate onto the monolayer, and this is what changes our band structure then. And the third one would be that our substrate is screening electrical charges inside our monolayer. At the moment, we are favoring this kind of theory. It becomes more clear when we look at what's called the dielectric constant, which gives an indication of the screening abilities of our material. So for silicon, the dielectric constant is roughly 12, for HBN it's 6, and for SiO2 roughly 4. And we see that while the dielectric constant diminishes, this E gamma K actually increases for the different substrates that we have seen. So to sum this up, conclude, well, this parameter E gamma K switches sign and is very important for the absorption or emission in monolayer TMDCs. We found that this E gamma K can be changed by a substrate through a dielectric effect on the order of a couple hundred millielectron volts. That means that yes, we can tune optoelectronics and the band structure by choice of substrate and hence changing the environment. Thank you very much.
So thank you, Enzo, for your talk. So if there is some question on the chat, otherwise you to study and to make your experiment, you use exfoliated 2D materials. And do you see, okay, I know it's a very fundamental work and very impressive result. Do you see some opportunity to translate or to develop the method of exfoliated material for fabricating devices at a larger scale than individual devices in laboratory?
Okay, so yes, we use exfoliation as a means of making our samples. The good thing about exfoliation is that you have high crystal quality. You usually have very small samples. The process, I feel at the moment, the way it is done is being done manually, and even in the manual, it's very hard to parameterize mechanical exfoliation. So I'm not sure it would be a means of building large scale monolayer systems or even bilayer systems for that matter. I really think that CVD, MBE, these kind of systems would be, at the moment, would be for large scale applications are probably more suitable. Even though, I mean, we just have to see what's up to come, because I've seen studies as well where they're able to exfoliate large scale monolayers, but the reproducibility, I'm not so sure at the moment.
Okay, and Jean-Pierre asked you a question. Do you have plan to move from exfoliation to CVD process flow?
So at the moment, we have a plan to look at MBE build systems. So not exactly CVD at this point, but yes, we want to go into another fabrication, means of fabrication. So we want to build heterostructures using MBE.
And he add CVD process flow for each 2D material, but transfer will be key. Okay, sure. Yes, it's really for all these 2D material development, they have shown very interesting properties. But as Pauline said, and you also mentioned, the key point will be probably to be able to elaborate these 2D materials, many types of 2D materials on large scale. And then another problem is also the contact issues. It's quite challenging to contact very well the 2D materials in comparison with a standard bulk semiconductor materials.
Do you mean electrical contacts in that case?
Yes.
Okay,
yes, exactly.
Because another point would be that, well, mechanical exfoliation gives very good crystal qualities. I feel that the CVD and MBE, they give better interfaces, basically. So for heterostacks, if you want to combine different 2D materials, then you have less contamination, and that's good as well. So it has to be a compromise between these techniques at some point.
Okay,
thank you.
But also cracks, bending, during transfer, sure, Jean-Pierre, there is a lot of issues with all these 2D materials. But I think they could make some breakthrough concerning the consumption of materials, and they have also very interesting properties. Okay, so if there is no more question, we can move to the next presentation. Laetitia, have you seen Lamia? She's connected or not?
Yes, I'm connected.
So you are connected, Lamia. Okay.
So I can share my screen.
Okay, so Lamia, I think you face some trouble with your computer.
Yes.
So now it's okay.
Now it's okay. Thank you.
Okay, so you can share your presentation and share your work concerning supply chain risk management methodologies for the nanoelectronic industry.
Thank you.
So you can go. Yeah, perfect.
Perfect. Thank you very much. So hi everyone. So thank you to be here. So my name is Moulidi Lamia, and I am an engineer and a PhD student in the CIRAG laboratory at Grenoble. So I will present you my research, which is about the methodologies for managing risks affecting the supply chain of the nanoelectronic industry. So first of all, why we will talk about the micro-nanoelectronics. In reality, it's a key sector in our daily life. So we have the research and development efforts that try to improve the performance of materials. And on the other hand, we have application sectors, automotive, communication, analytic, defense, and IoT that try to move this domain in the hive. So the application of this of micro and nanoelectronics affect our daily life. So it's important to secure their supply chain. I will explain you also why we try to secure it. We have two types of contexts. We have, I don't know if you can see me. If everyone see me?
See you? No, but we see your presentation.
Okay. So we have two types of context. So the first context is the external one, is the one that no one can affect it. So we have the increased demand in the application sectors. We have the use metals with constraint characteristics. As we see here is the byproduct characteristics, is that we don't have mine for every metals that we use. We have metals that are mined with other host, what you call the host metals. So they depend on the host metals. And the third parameter is that the quantity of raw materials that are used now and that we need for the future are not compatible with our need. So here we have a USGS picture that allow us to see the number of years of the availability of each metals. When we see this graph, we will see that lithium we have just for 10 years. These 10 years are calculated based on the demand or the actual demand. So if the demand increase, and we don't find other mines, so here we will have a problem. So one of the things that we will see here is the unavailability of these metals. The second type of context is the diversity of metals that are used. As we see here is just a simple example of the smartphone. We'll see, as we said, several metals from different countries. But also we have the complexity of the supply chain that allow us to manufacture this smartphone. So here we have the interaction between these two contexts that allow us to say that the industry is vulnerable. So we have several undesirable events, and it's not just a hypothetical thing. It's not a hypothetical conclusion. It's real because we have some crises that impacted the companies. One of the crises is the Sony Ericsson problem that one of their suppliers had a fire that are located in New Mexico, have had a fire, and the Ericsson company wasn't really ready to face this type of undesirable events, and we had a great and a huge financial impact. The second event that I want to talk about, which is a really important event, it's not about fire or about earthquake, but it's a geopolitical undesirable event. So we had in a geopolitical problem between Japan and China. And China, so to make a pressure on Japan, so what they did, they just made some restriction in their exportation of the metals. So then several industries of Japan had impacted. So then we had some geopolitical problem that may have impact a company, so then impact the manufacturing of product. So we need to see the whole context, so then we can secure our supply chain. Seeing all this, we ask a question: what is the best strategy to secure the supply chain of this industry? So we will begin with a state of art. We know that we had to assess the degree of the vulnerability of companies to supply risks. And we also have to develop tools to anticipate this supply risk, because we need to be proactive. We don't have just to say to face crises when they arrived. So we can manage these risks. How? First of thing, we have to identify them by asking some questions. So the practitioner or the company need to ask this question: what type of risks company are exposed to? Here we have an example: mine closures. So we have the mine is closed. And what is the impact? This is the cause. What is the impact? The impact is related to manufacturing. So the supply will cease. Second question. So here we have the scenario of risks. The second question that we ask: where are they located? So here we have a simple, as I said, a simple supply chain, just to illustrate my example. So we have our focal firm, which is situated in France. We have manufacturing of lithium-ion. The problem here is in the mine, in the mining steps, which is situated in China. So we don't have lithium. So here we have our hypothetical scenario of risks. The second question is how to measure. We have to measure this risk. So we have the probability that the mine will be closed. So here we have to try to define the probability that one mine in China will be closed. And we also have to evaluate the severity of this impact. When we say the severity of this impact, it can be about the amount of the financial impact on my company. After that, we have to see if this risk is acceptable or not. For me, it depends of the importance of this risk for my company. We have to treat it. Also, it depends on the evaluation. And also, at the end, we have to monitor this risk. Why? Because when we try to evaluate risks, it's at this time, at this point. But the context evolve and also my company will evolve. So we have to monitor, so to update my analysis. But when you see this way of doing, it's depend on the context, it depends on the objectives, of the tools that I will use to identify and evaluate, and the capacities of the company. We have financial capacities for the treatment and also the knowledge of the practitioner. So it's very subjective study. Here we will talk about the industries which just use metals. So at the point of this research is that the approaches that are proposed are not adapted to our industry. So the nanoelectronic industry, if they use this approach, it will not be well strong and it will not be really proactive. So we need to help them by adding other tools and other approaches, so then we can capture the reality of these undesirable events. So, for the nanoelectronic industry, what is the most important concerns? The most important concerns are the materials that are used. So, if we have uncertainties around these materials, these uncertainties arise from the context, as we said. So all this will have a domino effect. So the first supplier, which is mine, will not be available. So then all the other actors of my supply chain will be affected. So here, what we propose is to concentrate in the first steps of my supply chain, so then I can secure all. How? We have critical materials. Everyone learned or heard about critical materials, about in Europe, also on Japan, also in the United States. We talk about a list that countries try to specify them. But what do we really mean by this? In reality, material to be critical have two dimensions. First thing is have to be importance in use. How? If you want to evaluate this importance of use, we have to see one thing is the substitutability of these materials. If it is possible economically and technically. So if it isn't possible, so it's important. The second dimension that we have to say, if this material is important material, is it accessible or not? For the accessibility, what may impact my accessibility? Are the undesirable events that will break my supply chain so the material will not be accessible? The third thing that we have to see is the availability, so the amount of reserve that we have in our earth. So the amount of the reserve that we have for each metal. So this is important. So this is what we have to, this is the approach that the company had to use so then they can secure their supply chain. The process is simple. First of all, we will see the supply risks. What are all the risks that will impact, and also, as I said, impact the accessibility of material. So I have different indicators. And for each indicators, we have databases that allow us to measure these parameters. The second thing is the vulnerability. When I said vulnerability, I said also importance of use and also economical importance. It's all the same for the researcher. Also here, we have indicators. It can be economical indicators, substitutability indicators. So they can allow the company to measure the vulnerability or the importance of use of each materials. The third dimension is are not used in every studies. It's ecological risks. It's about the ecological impact. In reality, it depends on the culture of the company. So if the company wants or says, or for her, the environmental impact is important and make metals critical, so they have to use it in their process. So at the end of this process, we will get, or we'll have, a list of materials that are prioritized according to their criticality. So if we are a research in metallurgy, we can say just that the criticality is another parameters that characterize metals. It's like temperature of fusion, etc. We just have to add the criticality as another parameter that can describe the metals that we will use as a research development or as a company.
Lamia, just so you know, you have 1 minute left.
Okay, thank you. So here we have another, to illustrate our parameters, is that we have the HHE index, which this illustrates the concentration of producer of each materials. So the most is concentrated in one country, the most is critical for us. This is one of the supply risks that we had, and that the first approach cannot capture if we use it. So at the end, what we want to say is that we need to add the assessment of material criticality to the supply chain risk management by proposing what we had. It will be actionable practices, and also that we have consensual within the researchers. The second line of action. So now we know that the critical material is a great concept that have to be introduced and will improve the proactive actions. The second line is that the complexity of the supply chain depends on the choices that are made by research and development team. So we need to integrate also the supply chain risk, this critical material assessment into their practices. So by creating a methodology for them. So the advantage of this concept are two. The first is for research and development when we want to innovate and to design another product, and also help us to evaluate the vulnerability of the materials of the company to a certain materials. As a conclusion, so we highlight the usefulness of material criticality in capturing the external risk and the level of vulnerability of the firm. We also linked this assessment into the supply chain and how company can do it. And at the end, we link this assessment to the product designer process and also for the research development process. So for the future researcher are just to build this methodology that we have to balance between the practice that we actionable and that we conceptual, and we can capture all the reality. And thank you for attention.
Thank you, Lamia, for this presentation. So we have some question, and a very pertinent question from Jean-Pierre. Access to data is key to draw solid conclusion about the supply chain risk. What are the main difficulties to access to those data? Quantities on the market, price, accessibility, availabilities. Who provide information into the database you are talking about? What about transparency? How those databases are built in?
So the main problem that we had in this to apply this concept is the access of the data. But in reality, if we talk about the list of criticality in a region of our maybe European states or European Union or United States, it's a regional one. So we had some databases that can allow us to get some results like USGS that help us to have the geological data, so it's accessible, and also for research and development that want to create a new product and try to evaluate the criticality of materials that he used to create a new product. So here we can use USGS for the geological part, but the main problem is for firm is the visibility. So they have to make a more effort. So in interviewing all the supplier, so then they have to go to the mine. So they have to have a structure of their supply chain to the mine, and after that to access the other data, we have to use expert, the expert to get the data. It will be semi-qualitative or qualitative data. We will not have only quantitative data to evaluate it. I hope that I answered.
Okay, thank you, Lamia. So this will be a key data for your thesis.
Yes, it's for expert. Yeah. It's just expert, and also all what we had is also we have the HHE, the parameters that we can calculate it out by ourselves by using other databases. We have also Ecovian, which is that allow us to evaluate the environmental impact of each materials that are used in.
Okay, so currently we faced a severe sanitary crisis, as you know, and as you already seen in the literature, some impact concerning the supply chain of critical materials of this sanitary crisis.
So as when I did my research, the first thing is that even the industry were impacted. The level of this impact are less comparing to other industries.
Okay.
Even in the demand, even in the problems. In reality, when we have this as you said, this strategic because this industry is strategic. So what we will see and we will remark is that even the country will do more efforts, so then this industry will not be impacted at this level.
Okay.
I don't know if the message is.
Yeah. Okay. So thank you, Lamia. I think there is a comment from Bernard also, Jenny. In microelectronics, we tend to use very small amount of material compared to other technologies. For instance, magnetic memory, 50 kilo of platinum will be sufficient to produce magnetic memory in France for 10 years. Cannot we buy 50 kilo of platinum today when the supply is okay, put them in a safe and use them gradually as needed during the 10 years? If you have an answer, Lamia. Otherwise,
I didn't.
It's just to buy all the material you need for the next 10 years.
Ah, okay.
Especially when you need a small amount of platinum. But nevertheless, I think 50 kilo of platinum, it's a small amount of materials, but a big amount of money.
So what is the question?
The question is that if you buy the material when it is available, and you save it and use it when you need it, is it a good strategy for the industry, or is it possible that the industry will buy this material? It's a lot of money, and this money will slip somewhere.
So we have some companies that are some strategic stocks.
Yeah.
It's like stocks. So, and this strategic stock it depends on this evaluation. So if the material is important, if we know that if we don't have these materials, our product will not be manufactured. This is the strategies that several companies did. But if we know that in 10 years we will not have this, we will have some problems. So like GE, what they did for germanium, they changed they changed the structure of their product. So they use less germanium, and so then they change the technology to create their product. So when we know that the problem will be in 10 years, we have enough time to make some changes in our product design, so then in our supply chain and in the actors. So this is my answer. It's not just have this, because when we get this inventory, strategic inventory, is just for a short, medium term problems. But here when we say 10 years, it's a long term problem. So we can be proactive now and change it at this time by acting in the beginning of the process of the product designer.
Okay. So there are several exchanges in the chat, so you can follow the exchange in the chat. But I think, Laetitia, we have to move to the other session, piezotronic. I see it. Okay.